Hello everyone, I am Dr. Parameshwari, Assistant Professor, Department of Mathematics, Vardhaman College of Engineering. And in this video, I will explain about the complex power series. Now, complex power series is an infinite series of the form summation n is equals to 0 to infinity a n z minus z naught whole power of n. And if we replace n is equals to 0 to infinity, we will get the infinite series, that is a naught plus a1 in bracket z minus z naught plus a2 in bracket z minus z naught whole square plus so on. So, a n z minus z naught whole raised to n, and this is the complex power series, and here a naught, a1, a2 so on so are the complex constants. Now, the power series is an in powers of z. That is, this is the complex power series in a form of z minus z naught, and here complex power series in a form of z. That is summation n is equals to 0 to infinity a n z raised to n, and it is equals to, if we replace n is equals to 0, we will get a naught. If we replace n is equals to 1, a1 into z plus a2 into z power of 2 plus an into z power of n plus so on so. And here we will next discuss about the region of convergence of a power series. And here region of convergence of a power series is the set of all points z for which the series is converges. And here the series summation n is equals to 0 a n z minus z naught whole power of n, and this series, this complex power series is converges for modulus of z minus z naught value is less than r, and if it is diverges, modulus of z minus z naught value is greater than r. And here capital R is known as the radius of convergence, and the circle modulus of z minus z naught is equals to capital R, and it is the circle of convergence. Now, the radius of convergence, here the radius of convergence of a power series, and here complex power series summation n is equals to 0 to infinity a n z minus z naught power of n, and it is given by, and capital R. Capital R is the radius of convergence, that is limit, this one is the radius of convergence, limit n tends to infinity modulus of a n by a n plus 1. And in this complex power series, first we will discuss about the Taylor series. So, in Taylor series statement here, if f of z is analytic within a circle C with the center at z naught, then for any z in capital C, that is f of z here expansion is f of z naught plus 1 upon 1 factorial into z minus z naught into f dash of z naught plus 1 upon 2 factorial into z minus z naught whole square f double dash of z naught plus so on. So, up to the n power series here 1 upon n factorial z minus z naught whole power of n f power of n into z naught plus so on. So, this is the Taylor series expansion. Now, in the special case, in this Taylor series, if we replace the z naught value is 0, if we replace this z naught value is 0, then this Taylor series will converted into f of z is equals to, we replace z naught value is 0, that is f of 0 plus 1 upon z minus 0, that is z upon 1 factorial f dash of 0 plus z square by 2 factorial f double dash of 0 plus so on. So, z raised to n upon n factorial f power of n into 0 plus so on so. And if we replace z naught value is 0 in Taylor series, and this series is called as Maclaurin series of f of z. Already we know about the Taylor series expansion. Now, here we use the Taylor series expansion by solving some problems. Now, here I will take the first question, expand cos z in Taylor series about the point z is equals to pi by 2. That is, here first we will write the Taylor series expansion. So, Taylor series expansion, f of z is equals to f of z naught plus z minus z naught upon 1 factorial f dash of z naught plus z minus z naught whole square upon 2 factorial f double dash of z naught plus z minus z naught whole cube upon 3 factorial f triple dash of z naught plus so on so. And this is the Taylor series expansion. Now, in this expansion, we have to calculate each and every term, that is here in our problem, z point value is given, that is pi by 2. That is f of z naught means f of pi by 2. Let f of z here will consider as cos z. And in Taylor series expansion, we have to calculate f of z naught. That is, it is implies f of z naught, and here already z naught value is given pi by 2, that is here we take f of pi by 2. F of pi by 2 means here we replace the z value is equals to pi by 2, that is cos pi by 2, and we know the cos pi by 2 value is 0. And this is what f of z naught value, and in expansion of the second term we have to calculate f dash of z naught, that is we know the f of z value, and from this f of z value we take the first term derivation, that is the derivative of cos z is minus sin z, and in expansion we want f dash of z naught, and we have the z naught value is pi by 2, that is f dash of pi by 2 means in this minus sin z we replace the z value is pi by 2, that is minus sin pi by 2, and we know the sin pi by 2 value is 1, that is minus 1, and this is what the second term f dash of z naught, and in expansion we have the third term, that is f double dash of z naught we have to calculate, that is f double dash of z means once again the derivation of the f dash of z, that is the minus sin z derivative is minus cos z, and in this same as it is we have to replace the z in a place of z we have replace z naught, that is f double dash of z naught, that is we have the z naught value is pi by 2, and we know the cos pi by 2 value is 0, that is minus cos pi by 2, and it is equals to 0. Similarly, we calculate the f triple dash value, and we know the derivative of a cos z is minus sin z, that is already we have the minus value here, that is minus sin the minus is plus, means f triple dash of z, here we get the derivative is sin z, and now we replace in a place of z, z naught, that is f triple dash of z naught, that is f triple dash of pi by 2, means here replace in a place of z pi by 2, that is sin pi by 2, and we know the sin pi by 2 value is 1. Now so on, so we take the derivatives. Now totally these derivatives we have to replace in a Taylor series expansion, that is f of z, and we know the f of z. F of z here we are taken as cos z, that is here we replace the f of z is equals to cos z, that is f of z cos z, and it is equals to, here we have the expansion f of z naught. F of z naught value is we got it as 0 plus, and the second term expansion we have z minus z naught, that is z minus z naught upon 1 factorial f dash of z naught, and we have the f dash of z naught value is minus 1, that is here we replace z naught, f dash of z naught value is minus 1 plus second one z minus z naught whole square upon 2 factorial second derivative f double dash of z naught, and f double dash of z naught value we got it as 0, that is here we replace 0 plus third derivative z minus z naught whole cube upon 3 factorial, and here f triple dash of z naught value we got it as 1 plus so on. So now in this we replace the z naught value, and we know the z naught value in our question it is given as pi by 2, that is here I will replace the z naught value. Therefore cos z expansion using the Taylor series in a powers of z minus pi by 2, that is minus z minus pi by 2 upon 1 factorial, and this is totally 0 plus z minus z naught value is pi by 2 whole cube upon 3 factorial minus so on. So, and this is the Taylor series expansion of the cos z in a form of z minus pi by 2. Now we will discuss about the second problem, that is in second problem we will discuss about the radius of convergence. Now in second question, obtain the expansion of z minus 1 upon z square in Taylor series in a powers of z minus 1, and we have to determine the region of convergence. That is, if we obtain the expansion of z minus 1 by z square means, and this function we have to assume, that is first here I will assume f of z is equals to z minus 1 by z square, and here we have to expand this function in powers of z minus 1, that is here I will consider the z minus 1 value is equals to w, that is if we consider the z minus 1 value is equals to w, that is the z is equals to w plus 1. Now f of z here I will write z minus 1, and we have the z minus 1 value is w, that is w upon z square. We have the z value is w plus 1 or else 1 plus w, that is 1 plus w and whole square, that is whole square, and this is f of z in a form of w. Now we know the expansion of 1 plus w, that is here I will write w, and this I will take into numerator 1 plus w whole power of minus 2. Now here I will expand this using the binomial expansion formula, w in bracket 1 plus w whole power of minus 2 expansion using the binomial expansion, that is 1 minus 2w plus 3w square minus 4w cube plus so on. So now this expansion we multiplying with the w, that is a w into 1, w minus w into 2w, 2w square plus 3w cube minus 4w power of 4 plus so on. So, and this is the f of z expansion in a power of w. Now here I will write this f of z, this series I will write in a form of a summation, that is a summation n is equals to 0 to infinity minus 1 power of n into n plus 1 and w power of n plus 1. That is here I am writing this expansion. If we replace n is equals to 0, minus 1 raised to 0 and 0 plus 1, 1, w raised to 0 plus 1, that is here we will get w, and if we replace n is equals to 1 we will get minus 2w square. If we replace n is equals to 2 we get 3w cube. That is this series here I am writing in a form of summation. Now after writing the summation, here I want to calculate the radius of convergence. That is, in this expansion I will compare this power series, complex power series into an. That is here we will get the an value is, complex power series is in a form of a summation n is equals to 0 to infinity an into f of w. That is this value I will write first, summation n is equals to 0 to infinity minus 1 raised to n plus 1, and we know the w value, that is firstly we consider the w value is z minus 1, that is here I will write the w is equals to z minus 1 whole power of n plus 1. That is, this is the expansion of the f of z in power of z minus 1. Now here I will compare the an value, where an is equals to minus 1 power of n into n plus 1, and this is the an value. Now here I want to calculate the radius of convergence, and we know the radius of convergence formula, a radius of convergence. So radius of convergence is denoted as capital R, and it is equals to limit n tends to infinity modulus of an upon an plus 1, and this is the formula of radius of convergence. Now in this radius of convergence I will replace the an value, and also in place of n we replace n plus 1, then we will get the radius of convergence. That is limit n tends to infinity modulus an. We have the an value is minus 1 power of n into n plus 1 upon an plus 1, that is in a place of n we replace as n plus 1, we will get minus 1 power of n plus 1, and in a place of n plus 1 means plus 1 plus 1 plus 2, that is n plus 2, and if we cancel minus power of n minus 1 power of n, then we will left here limit n tends to infinity modulus of n plus 1 upon n plus 2. Now here we want to evaluate this limit. If we take n common, 1 by n, and if we take n common in denominator, 2 by n, that is 1 by n means here we have the n value is infinity, that is 1 by infinity we will get as 0, that is here we replace, we will find the value of limit is 1, and this r value, this is the r value, that is the radius of convergence. Now here I will write the region of convergence. The region of convergence is modulus of z minus 1 already is given, and it is equals to less than 1, and this is the region of convergence. Therefore, by using the Taylor series, f of z here we got the expansion. What is f of z here we got? F of z is equals to summation n is equals to 0 to infinity. This one is f of z value, that is summation n is equals to 0 to infinity minus 1 power of n into n plus 1 and z minus 1 power of n plus 1, and this is the radius of region of convergence. Modulus of z minus 1 is less than 1, and this is the Taylor series of the second problem. Now like this we use the Taylor series expansion, we will solve problems. Thank you.